Population growth. A powerful tool to study population growth pattern is survivorship curve. Type 1 curve has high survival rates in early and middle life due to the stable environments they live in. They experience a rapid decline in survival rates in later life and a high mortality in old age. Type 2 curve is characterized by a constant mortality rate throughout the animal's whole life, regardless of their age. The curve is mostly linear. In type 3, animals have the greatest mortality rate early in life, but once they survive their early age, they start to have low mortality rate for their later life.
The first type of population growth is exponential growth, in which a population grows at an increasingly rapid rate in proportion to the growing total number or size of the population. Bacteria experience exponential growth, and as you can see from the graph, initially there is a lag phase in which there is very little growth. However, the population will begin to divide very rapidly until it levels off and eventually begins to decrease due to negative density effects. This means that the population will be too high, causing overcrowding and limiting resources. Our selected species experience exponential growth and are part of type 3 survivorship curve since they grow rapidly at first before eventually dying off. They live in unstable environments, and these unstable environmental factors continually reduce population size before it can reach carrying capacity. This leads to rapid reproduction in a population. Logistic growth occurs when the rate of growth is proportional to both the existing population and the amount of available resources. Otters are an example, reproducing as resources and other density-dependent factors are available. Eventually, they reach a carrying capacity and enter a stable equilibrium state. For case-selected species, population size is steady around carrying capacity due to stable environmental factors, and there is much less rapid reproduction. This is the equation for logistic growth, in which the change in population over change in time is equal to the intrinsic rate of increase multiplied by population size. The carrying capacity, K, causes the graph to level off.
This is an inverse curve of the previous graph depicting logistic population growth. Some of the key points are that at Rmax, the highest rate of increase in the population size is very low and is below the minimum viable population. Once the MVP is reached, R continues to be positive, and the population continues to grow exponentially, as long as the number of individuals in the population does not hit K. Once K is reached, R equals 0, so the population stops growing exponentially, but may continue to grow at a slower rate. Once K is surpassed, the population is now high and R is negative, so the population size begins to decrease. Populations do fluctuate once carrying capacity is reached, leading to population cycles, which are alternating periods of high and low abundance of populations due at regular intervals. Delayed density dependence also causes fluctuating numbers in a population. Imagine that in a population of otters, the carrying capacity is 500. It is highly unlikely that the population will stay perfectly at 500 otters. The numbers will most likely be above or below 500 depending on how many die and are born. This equation modifies the logistic equation to take into account these time lags. A common problem facing populations early on is the small population paradigm, which usually results in an extinction vortex due to the lack of reproductive potential. This initial decrease in the rate of proliferation can be mitigated by the Alley effect, which refers to the impact that increased density can have on a small population. If all the individuals of a population are clustered together rather than spread out over an area, individuals are more likely to run into each other, giving the population a better chance to increase in size. The costs associated with inbreeding still apply while the population is small, but this is preferred over not reproducing at all. Density dependence rescues populations from the small population paradigm until they reach the minimum viable population. At this point and beyond, the population is subject to normal logistic growth patterns.